Hey math fans, Alex here, and welcome to Probability Theory. This is my first lecture, hopefully of many. I'm just testing out the waters here, and let's see how this goes. So section 1.1 is on probability and relative frequency. By the end of this lecture, I want you to be able to differentiate between experimental and theoretical probability, as well as connect the dots between the two using the law of large numbers. And also I want you to understand how simulations allow people to determine experimental probabilities. That will probably be its own separate video where I walk you through some code. But for now, let's get started. So the first thing that we need to discuss is what an experiment is. So when I use the word experiment, what I'm talking about is basically a situation in which there are multiple different outcomes that we can enumerate as follows. Maybe that's 1, 2, ... all the way to capital N. And we refer to all these possibilities as the sample space. Okay, and the sample space is basically the set of all possible outcomes of an experiment. Okay, so you really can think of this as a set, which is just a collection of objects. For most purposes, and I believe probability theory, we're going to consider those to be numbers, but really sets can be collections of whatever you want, and that's a sample space. Now, for our setup, we're going to go ahead and assume that there are capital N possible outcomes. Okay. With the following properties. First, all of them are going to have the same likelihood to occur. Okay, so outcome number 1 is just as likely as outcome number 357. Okay, so we call this equiprobable, is the word for that. And the second condition we have in our experiment is that there is no overlap between any of the outcomes. You cannot have two outcomes simultaneously occurring. You either get outcome 1, outcome 2, ... or outcome N. Okay, so the word for that we're going to use, mutually exclusive. Okay, now that we have all that terminology kind of out of the way, we can define an event. So, an event is a collection, or more specifically, a subset of at least one outcome in the sample space. Okay, so imagine that maybe you want the probability of event A, and event A consists of either outcome number 1, 2, 5, or 7, and there are 10 possible outcomes. Okay, so as long as at least one of those outcomes is selected, that is an event. All right, now with all that terminology out of the way, we are finally ready to define probability. More specifically, theoretical probability. So, we're going to go and say that the theoretical probability of an event, which we'll label with a capital letter, usually capital A, occurring is we're going to go and define it by this formula here. We're going to say P of A is going to equal capital N of A divided by capital N. Okay? Now, first things first, if this reminds you a little bit about function notation, right? This P of A, the F of X, good, it should. Probabilities can really be thought of as functions where you're inputting an event and you're outputting a number between 0 and 1, if you want to think about it like that. But nonetheless, what is that notation? That notation refers to the number of outcomes that result in A occurring. Okay, and this bottom number without the A does not depend on any events. This is just the exactly as we defined it up here, right? This is the same N, and it is the number of total outcomes in the sample space. And that's it. That's probability. End of lecture. No, just kidding. The tricky part is really finding these numbers. These numbers are incredibly difficult to find sometimes. Okay, just as a quick example, let's suppose that I have a room filled with gas molecules, and there are, of course, in the billions and probably way more gas molecules. And I want to know the probability of some of those gas molecules being arranged in a certain way. Well, how many ways are there to arrange billions and billions of gas molecules? That is a very difficult question to just come up with the answer on the top of your head. So it's really difficult, and we're going to be spending a lot of time very carefully constructing how to find those two numbers. But just to give you some quick examples, okay, so let's suppose that standard deck of cards and the first thing to kind of point out here is, does a standard deck of cards satisfy these two conditions? If I just draw a card and I call that my experiment, well, every card, if it's shuffled properly, has the same likelihood to occur, and there's no overlap. I can't draw a 3 of diamonds and also have it be the 5 of hearts at the same time. Okay, so in a standard deck of cards, where capital N is equal to usually 52 without jokers, okay, we're going to go ahead and let the event A be, let's see, drawing a red card, just any red card. And we'll let event B be drawing a club. And even C be drawing the 3 of hearts. Sure. Let's just do some quick probabilities then. So the probability of A occurring is the number of possible ways that A can occur divided by the total number of outcomes. Well, there are 52 outcomes. We already figured that out, so we can go ahead and replace that with 52. Then how many ways are there to draw a red card? Well, how many red cards are there? Well, usually it's half black and half red, so there are going to be 26 of them. Okay. The probability of B occurring, well, how many clubs are there? Well, there are 4 suits that evenly divide the 52 cards. So if you do the math and cut 52 into 4 pieces, each piece is going to have 13. And there are still 52 total cards. And what's the probability of drawing the 3 of hearts? Well, there's only 1 3 of hearts in a standard regulation deck, so that probability is 1 divided by the 52. So that's just a quick example. And this is theoretical probability. Okay? All right. Now, suppose you perform an experiment with some number of trials that are going to be fixed or a constant value. And we can define the experimental probability. And the experimental probability, which we're going to underline, of an event A occurring is given by the following. It is going to be little n of A divided by little n. Okay, so what's the significance of those letters? Well, little n of A is going to refer to the number of observed trials where A occurs. Okay, so if you physically flip 10 coins, 10 fair coins with either heads or tails, and event A is maybe rolling a heads, then how many times in your 10 trials, how many trials did you get a heads? Okay, and this is, of course, the total number of trials. Okay, so that is theoretical versus experimental. I'll just kind of scroll up to review. So theoretical probability, we take all these outcomes, which are equally likely to occur, and there's no overlap between them, and we figure out the total number of outcomes that result in your event, and we divide that by the total number of possible outcomes. Hopefully you understand why this number has to be between 0 and 1. It's impossible for an event A to be more outcomes than are in the sample space. That's just not how we defined it. An experimental probability involves trials of you actually performing an experiment and observing how many of those trials A occurs. Okay, so you might be wondering then, is there a connection between these two probabilities? And the answer is yes. So, we're going to go ahead and say, for large n, remember n represents the number of trials. For large n, we have that the probability of A occurring, that theoretical probability, is on the same level as this experimental probability. So this is really the key here for large n. And this gets into a discussion about the law of large numbers. We're going to have to do that for another time, but just kind of keep that in mind. So just to kind of review everything that I wrote on the board, maybe I'll do it in blue here. So this is the theoretical probability. This is the experimental probability. And this symbol technically means is asymptotic to. Really just means that for large enough n, it's on the same level, plus or minus a tiny bit. Okay, but for those of you that have taken calculus, you should kind of understand what it means to be asymptotic to something else. That's really the definition of a horizontal tangent, which in calculus we can express as the following. we can say that the probability of A is equal to the limit as little n approaches infinity. That's what a horizontal asymptote is, right? It's a situation in which your graph kind of approaches a certain y value as your x goes to infinity. Well, as your number of trials goes to infinity, the experimental probability is not going to vary as much, and it's going to approach the theoretical probability. Okay. Now, in the next video, I'm going to try to show you how to write some basic code in Python that's going to mimic experimental probabilities. Because I very well don't want to flip 10,000 coins when I want to figure out that the probability of getting a heads is 1/2. I can write a computer program in minutes and just get 10,000 trials instantly. But for now, there is one more thing that I want to mention before I close off this video. That's another example. This is kind of something I want you to think about before the next video. It's going to be de Maisre's paradox. So probability theory has a very interesting story because it really started with gambling. People with gambling addictions really wanted to win. And so, and I believe this was, my gut's telling me 16th century, maybe a little bit of the 15th century, probably more 16th, 17th century. People in France decided to gamble, and this guy de Maisre wanted specifically to figure out this one game. Okay, so de Maisre was a French gambler who played a game in which 3 dice, since it's plural, I think we use the word dice. 3 dice are tossed, and the sum is calculated. Okay, so for example, if I roll 3 dice and I get a 2, a 1, and a 1, well, then I add those together and my result would be 4. Okay. So he discovered experimentally, there's that word again, experimentally, that it was more likely to get a sum of 11 instead of 12. Okay, so you might be thinking to yourself, okay, I don't really know what the probability of getting a sum of 11 or 12 is. That's fine, but here is his reasoning why getting a sum of 11 and 12 should actually be the exact same. Here is his reasoning. So his reasoning on why they should have the same probability. Okay, so here's his reasoning. Let event A basically be getting a sum of 11, and let event B be getting a sum of 12. Okay, well, then A occurs in 6 ways, and I'm going to write them as ordered triples. okay? But you can also count the number of ways that B occurs. And you actually also get 6 ways. So this is like the weakest form of a paradox in that he's just kind of missing some information. Needed to kind of make sense of this contradiction. It seems like a contradiction because he observed that it was more likely to get a sum of 11 instead of 12, but, both getting a sum of 11 and 12 can both occur in 6 ways, and here are the ways. So what's he missing? So exercise for you. What is Damer missing? We will explore that in section 1.2. Thanks so much for watching.